Today we're solving problem 18 from the AMC 10B of 2022. So we consider systems of three linear equations with unknowns x, y, and z. A of 1x plus b of 1y plus c of 1z is 0. A of 2x plus b of 2y plus c of 2z is 0. A of 3x plus b of 3y plus c of 3z is equal to 0. And now in brackets, where each of the coefficients is either 0 or 1, and the system has a solution other than x equals y equals z equals 0. For example, one such system is all of this, where with non-zero solution of 1, negative 1, and 1 of x, y, z. How many such systems of equations are there? The equations in a system need not be distinct, and two systems containing the same equations in a different order are considered different. For this problem, we're going to use matrices. We let M of 1 be equal to the set of A1, B1, and C1. Same thing here. We let M2 be equal to A2, B2, and C2. Now we have M3. This is a group of A3, B3, and C3. So we have these three matrices here. So we want to find how many such systems of equations are there that successfully make this system of equations work, I guess. We have to split into cases for this problem. The first case being where M1 is equal to M2 is equal to M3. So they're all equal. We were given that, these are split into, where is it? So we were given that they're split into zeros and ones. The coefficient is either 0 or 1. So let's just take a random set here. Since these are all equal, let's just look at this random one. This is either 0 or 1. This is 0 or 1, 0 or 1. And this applies to all of them, but we're just taking this case, for example. So let's take this random case where all of them are the same. So 2 times 2 times 2, because there's two numbers here, 0 and 1. 2 times 2 times 2 will give us 8, which is the solution to the first case in this problem. Alright, so we solved for one of the cases here. This has 8 solutions. Now we have to move on to the second case here. The second case is where so I'm just going to write it out here. Where two of the matrices, let's call them M1 and M2, they are equal but not equal to the third matrix. This is I'm just writing it like this, but it can be switched around two other ways. So the amount of ways this can happen. Let's start with M1. M1 has 8 solutions. M2 has also 8 solutions, or I'm just going to write the same amount of solutions here. Now M3, this is a peculiar thing. Well, this would have 8 solutions, except you have to subtract that one solution from that M1 because it's not equal to it. This is 7. So now we can multiply that together. 8 times 7, 56 solutions, or cases here. But this is just for this specific case where M1 is equal to M2, but it's not equal to M3. This means that basically what I'm saying is that these matrices can be switched around 2 more times, or you have to multiply by 3. So 56 times 3, This is 168. So we have solved for the amount of solutions, I guess, for the second case. All right, so moving on to the third case. Third case, this is where all the matrices are not equal to each other. Is not equal to matrix 3. Well, there's actually a bit of there's subsets inside this possibility or case. The first case, well, one of them has bound to be equal to a set where it's 0, 0, and 0. Well, when this is possible, what we do is so this is 8 or 2 cubed. That's the solution when all of them are equal to. You have to subtract, 1, this is 7. But now 8 minus 2 is 6. So we have these new numbers because you subtract it because they're not equal. Now, once again, 7 times 6 is 42. But once again, we're not done yet. We have to multiply 42 by 3 because it can be switched around 2 more times. So this is 126. So we have solved for this subset of this case where M1 is equal to 0, 0, 0. This is 126. So, now the second subset of this case number 3, this is when M1 plus M2 is equal to M3. Two matrices added together is equal to the third matrix. Well, let's see here. What did we miss? Well, not what did we miss, but when M1 is, let's say, 1, 0, 0, for M2, 2, there's a lot of possibilities. 3, there's 0, 1, 0. There's, let's see here. There's 0, 1, 0, 0, 0, 1. And our last one, 0, 1, 1. So we have 3 cases right here. 3 cases. This one can be moved 3 times, and since the question says that even if the equation is the same but is moved around in a different order, that counts as a different case. So we multiply it by 3 because this one can be moved around 2 more times. So this is initial 3. 3 times 3 is 9. But now we're missing one more case. We've had it when M1 is 0, 0, 0, M1 is 1, 0, 0. Now we have to actually find the case where M1 is equal to 1, 1, 0. Well, right here, there's only there's only either 1 or 2 possibilities for M2. It's only 0, 0, 1. Right there. But once again, the same logic here applies now because it could be this thing can be moved around 3 more times. So this is 1, but now there's 3 possibilities here. So 9 plus 3 will yield 12, which is the amount of possibilities for these 2 cases combined. So we have our solutions here. For solution 1, or case 1, we have 8 as our solution. For case 2, we have 168 as our solution. And for case 3, we actually have 2 numbers, 126 and 12. So basically, you get the answer by adding all these numbers up to get our answer, which is 338.